Hello, everyone, and welcome back to Met Zone African Motives. We are still on grade 10 physical sciences, term 1. So, we want to continue from where we left from our first topic. So, on our first video, on our video series, we were discussing about pulses. So we took time to describe what a pulse is. We took time to give and state the features of a pulse. We took time to describe how pulses they interfere, where we were describing the principle of superposition. Now we now want to dive deep into what we refer to as waves. As we might remember, we say that a pulse is just a single disturbance that occurs within a medium. But now we want to start looking into what if we have a series or else a repeating what disturbance. What if we have a series of repeating what disturbances? What do those become? So you would see that if it is only a single short disturbance, it becomes a pulse. But if we are having a series of pulses or else a series of repeating disturbances, that is what makes what we refer to as a what? As a wave. And also, we would know that a wave carries energy, but however, it does not move matter permanently. So this picture that you can see here, it's an example of what we refer to as a what? As a wave. Where a wave is defined as a repeating disturbance that transfers energy without moving matter permanently. So you would actually get to note that a wave is a train of pulses. So would actually call, or else in summary, we would actually get to say that a pulse is one bump, whilst a wave becomes a train of what? Of bumps. So now I want us to dive deep into what we refer to as waves. We want to start classifying them. We want to start describing them in according to different types. So we have got two classes of waves. The most common one is what we refer to as mechanical waves, where we have got longitudinal waves and transverse waves. And then we have what we refer to as electromagnetic waves. So the difference between these two is that the other one requires a medium and the other one does not require a medium. And we say that a medium is just a fancy word of calling stuff like what? Water, ropes, as well as air. So we are saying that mechanical waves, they require a medium for them to propagate. Like for example, you would have your sound waves. They require air to actually get to propagate, or else they can actually get to what? To propagate through a certain medium. And then when it comes to water waves, they also require water to propagate. So we are saying that mechanical waves, they require a medium. They require particles of the medium to transfer or else to relay through the waves. But when it comes to electromagnetic waves, these ones, they do not require what? They do not require a medium. And the examples that fall under electromagnetic waves is what we refer to as the electromagnetic spectrum, where you would be having your radio waves, your ultraviolet rays, your X-rays, infrared, microwaves, as well as visible light. So we would actually like to start with defining mechanical waves so that we can be able to look into transverse waves as well as go into what? Into longitudinal waves. And then once we are done with mechanical waves, that's when we can be able to now get to start looking into what? Into electromagnetic waves. So under mechanical waves, as we have said, we say that these ones, they always need a medium, which is materials like air, water, rope, or else solids. And these medium, they carry energy, not matter. So we are saying that the particles of the medium, they transfer our energy. So how do mechanical waves form? So every mechanical wave starts as a vibration, which means that one particle of the medium gets disturbed through vibrations, and then it passes the energy of that vibration or that initial vibration to the next. So it's more like we are relaying energy from one particle to another. So we have got a single disturbance of a particle that moves up and down, and it actually gets to relay that same motion to another particle which moves up and down or else back and forth. If we have a series of particles, we would actually get to have a continuous repeating disturbance that we refer to as a what? As a mechanical wave. So we are saying that mechanical waves, they start as a vibration of one particle which actually gets disturbed and passes the energy to the next. So the examples of mechanical waves, as we have stated, are transverse waves, where we would actually get to see the transverse waves through ripples on water surface. Take for example, if you actually get to drop a paddle in your water surface, you would actually get to start seeing some vibrations which are shown by ripples of water. And then we have got what we refer to as longitudinal waves, where these can actually be classified through the movement of what? Of sound waves, or else we can say the propagation of sound waves in air. Now, let's look deep, or else let's now start to explain fully what we refer to as transverse waves. What is the difference between transverse waves? What is the difference between transverse waves and longitudinal waves? So you would see that what we refer to as transverse waves, these are waves where the particles of the medium, they get to move up and down while the wave is moving forward. Or else we get to say that the particles, they move perpendicular to the what? To the wave motion. So you would see that the particles of the medium, they would actually be displaced up, and then they would later come down, while least the wave motion is what? Is moving forward. So you can see that the direction of the what? Of the disturbance, or else of the displacement of the particles, would be up, whilst the direction of the wave would be horizontal. So you would see that the angle that is made in between these two directions would be a 90-degree angle. That's why we would call them what? Perpendicular waves, or else waves that have the particles of the medium moving perpendicular to the direction of the wave. So that is what we refer to as what? As transverse waves. So this is an example of a transverse wave, where we would note that we have got what we refer to as a crest, and what we refer to as a trough, and what we would refer to as a what? As a wavelength, and what we would refer to as an amplitude. Now let's actually get to look into the key features of what? Of a transverse wave. So you would see that within a transverse wave, you would be having these peaks, or else these highest points. So the highest point of a transverse wave is what we refer to as what? As a crest. The highest point of a transverse wave is what we refer to as a what? As a crest. So now, if we are to say that the crest is the top of the rise of a hill, then we would actually get to know that the lowest point, or else the valley of the hill, becomes our trough. So the lowest point of a transverse wave is what we refer to as the what? As the trough. So the crest becomes the peak, whilst the trough becomes the valley, or else the lowest point. And then now the maximum displacement of the particles of the what? Of the media within which the wave is propagating is what we refer to as the amplitude. That distance within which the particles are displaced, the maximum distance, it becomes the what? The amplitude. So the amplitude is the maximum distance a particle of the medium moves from its rest point. So we would actually get to assume that our particles, they are at equilibrium or else at rest when they haven't been moved, or else when they are not vibrating. Once there is a vibration or else there are some ripples, then we know that our particle would be displaced to a certain distance. That maximum displacement becomes our amplitude. And then now we would have what we refer to as the wavelength. The wavelength now becomes the total distance moved by a what? The total distance moved by the wave, or else it becomes the total distance between two successive points in phase. That can be a crest and the following crest, or else a trough and the following trough, or else let's say our starting point and then a complete move which forms a cycle that becomes the total distance, or else it forms the what? The total distance, or else any distance between two successive points in phase. It gives us what we refer to as what? As the wavelength. That being said, now we can now actually start defining the meaning of what we refer to as either the amplitude, the wavelength, period, and frequency when it comes to the what? To the energy of the wave. Because now we said when it comes to a wave, the particles are actually carrying or relaying energy from one particle to another through the propagation of the wave. So the wave is actually carrying what? Energy. And the displacement of the particles, they are just temporal. Now, we are now saying that the bigger the amplitude, it simply shows us, or else it tells us how much energy is being carried by that wave. So the total amplitude, it gives an indication of the what? Of the maximum energy being carried. So the greater this amplitude is, the greater the energy is being carried. But however, mind you, the amplitude has nothing to do with how fast the wave is moving. So what determines how fast the wave might be moving? This is when we now start looking into the distance that is being moved by what? By one wave. So we are saying that the distance between two crests or troughs, or else what we refer to as the wavelength, becomes the distance in which one complete wave moves. And the time it takes to move that one complete wave is what we refer to as what? Is our time period. Now, the number of waves that moves or else that are passed through 1 second becomes what we refer to as what? As frequency. Therefore, we've got a relationship between our frequency and our time period, which is given by the equation which says frequency is equal to 1 over the time period, where we are saying that this is the number of what? Of waves that passes through per unit 1 second. Now the frequency also gets to determine the amount of energy that can be carried by the what? By the wave as well. But also the frequency now later informs us on something that we refer to as the speed of the what? Of the wave. But before that, let's define what speed means in relative terms. We know that speed refers to the distance within which the wave is traveled per unit time. It is simply the measure of how quickly the wave pattern spreads from one point to another. After we've known those terms, now we want to look into what we refer to as the wave equation. So the wave equation is simply a formula that gives us the relationship between our speed of the wave, our frequency, and our wavelength. So we are saying that the distance between two successive crests becomes one wavelength. And this one wavelength, we are saying that the time it takes to move that one wavelength becomes our time period. If that is the case, we are saying that speed itself is the distance traveled per unit time. And we are saying that the distance that is traveled by one wave, it becomes the wavelength. And then we are saying the time taken to move this one complete wave becomes our time period. So we are simply saying that our wave speed can be given by what? By our wavelength divided by the what? By the time period, in accordance to the definition of our wavelength as well as our period. Now, if that is the case, we also know that our frequency can be given by 1 over time period. Now, look at this wave equation that we have written, where we have said the speed is given by what? By the wavelength over the time period. Now, if I'm to factor out my wavelength, I will now be left with 1 over t. And we said 1 over t becomes our frequency. This simply translates to the theorem which says that our wave speed can be defined as the wavelength of a wave times the frequency of the wave. This is what we define as our what? Our wave equation, where we are saying that the speed of, or else the total speed of a wave can be given by the what? By the frequency times the wavelength, where we are saying that the wavelength becomes the distance that is in between two successive points which are in phase, or else it becomes the total distance traveled to complete one wave, where we can see that this becomes half a wave and then this becomes half a wave. If we are to combine these two halves, they become one complete wave. So the total distance moved from point A to point B becomes the total distance moved to complete one wave. That becomes our what? That becomes our wavelength. Or else the distance in between two crests or else two troughs, that becomes our what? Our wavelength. And then the total time that it takes to move from the initial point to the last point, or else the total time it takes to complete this one wave, that becomes our time period. If that is the case, 1 over our time period gives us our frequency. And therefore, if we are to say our wave speed is equal to the what? To the wavelength divided by the time period, it simply gives us wavelength times 1 over t, which is our what? Our wavelength times frequency. And that becomes our what? Our wave equation, which is to say wave speed is given by the what? By the total frequency times the total wavelength. So that is what we refer to as the what? As the wave equation. So this wave equation, it applies either it is to transverse wave or else it is to what? To longitudinal waves. Either it is to do with mechanical waves or else it is to do with what? With electromagnetic waves. The wave equation will always be given by V is equals to what? F times lambda, where V represents the what? The wave speed, where this represents the wave speed and F represents the frequency of the wave, and then this represents the what? The wavelength. That is what we refer to as the what? As the wave equation. Now, after we've described and we've tried to give key features of what we refer to as our what? As our transverse wave, I brought you a question which was from the question paper of what? Of this was KZN. No, it was actually from Northwest. It was a question paper from Northwest which was written in November 2024. So this was a question paper from Northwest which was written in November 2024, where they were asking information to do with what? With transverse wave. So now we want to check our comprehension, if we have understood what we define as a transverse wave, and what we define as the amplitude, and what we define as the wavelength, and what we define as the period of the wave, and how we calculate it, and how we identify it if we are given a graph. So now let's answer the following question. So question number 2 was saying, from the given diagram above, which represents the propagation of a transverse wave that was produced by a certain source, define the term a transverse wave. So we say that a transverse wave, this is when particles of the medium move perpendicular. This is when the particles, they move perpendicular to the direction of the wave motion, to the direction of the what? Of the wave motion. And what does this mean? It means that if the wave motion is in that direction, it is moving horizontal towards the right, which is it is moving forward, you would get to see that the displacement of the particles would actually be up and down, meaning to say that they will be moving perpendicular to this direction. There will be a 90-degree angle in between the direction of the particles of the what? Of the medium, as well as the wave motion. That is what we refer to as the what? As the transverse wave. So we know that our transverse wave, it actually moves up and down, and then it can also move down and up, or else up and down. That is what we refer to as a what? As a transverse wave. So that is what we simply refer to as a transverse wave according to the definition that we have given earlier. So now, they were saying write down the amplitude in meters of the wave. Now, what is the amplitude of a wave? This is the total displacement from the position of rest, or else from the equilibrium position. So the distance moved by the particles of the wave, that is to say the maximum displacement of the particles of the wave. So it simply means that this is the rest position, and this is the what? The maximum position in which our particles would actually get to reach when they are what? They are displaced. So what becomes this this total what? Displacement. So you can see that at peak here we are having what? 40 centimeters. So our particles will be displaced a distance of what? Of 40 centimeters. So our amplitude here was going to be equal to what? 40 centimeters. But the question said in meters. So we know that they are 100 centimeters in a meter. So if you say 40 centimeters divided by 100 centimeters, you would get 0.4 meters. So our amplitude here was just going to be equal to what? 0.4 meters. Now the following question is saying, determine the period of this wave. Determine the period of this wave, given that our x-axis represents our time in which we are counting the movement of the what? Of the wave. So we would know that the time period becomes the time between two consecutive what? Successive points in phase, or else the time to complete one wave. So it's either from here, which is from 0 up until there. That's a complete wave. That is what? From 0 to 8 seconds. Or else from this crest to that crest. That means that is from 8 to 16. 16 minus 8, it becomes to say that we have got 8 seconds. We have got 8 seconds. So we are saying that we are taking 8 seconds to complete one wave. That becomes our time period. So our time period was going to be equal to what? 8 seconds. And then now they are saying if the distance d on the diagram is 0.9 meters. Now let's look at the distance d. So you can see that the distance d is actually coming from what? So I would say that the distance d is actually from here to there. This represents the distance from one trough to the next trough. And that gives us what? This gives us our wavelength. So you can see that the distance d is simply equal to our what? Our wavelength. So this distance d represents our wavelength, and they are saying it's 0.9 meters. So the distance between one trough to another is what we refer to as our what? As our wavelength, or else from one crest to another. Now they are saying, what is the name of the physical quantity given by the distance d? It becomes our what? Our wavelength. And then they are saying, calculate the speed of the complete wave as shown in the diagram above. What becomes the speed? What becomes the speed? We said that speed can be given by what? Speed can be given by the distance moved per unit time. And we say that the distance that we move to complete one wave becomes our wavelength. And then we say that the time it takes to complete this one wave, it becomes the time period. Now, what is our what? What is our wavelength? Is given on this question, they said our wavelength becomes what? 0.9 meters. And then what becomes our time period? We've determined our time period to be 8 seconds. So we were just supposed to say speed there is equal to 0.9 meters divided by 8 seconds. And that was going to give us what? We were now just supposed to go on and punch in our calculators, which is to say 0.9 meters divided by 8 seconds was going to give you what? It was going to give you 0.1125 meters per second. That is what you were simply supposed to do there. So that is all that you need to know in regard to what? To transverse wave. So I want us to meet on our next video, when now we will be now diving deep into longitudinal waves, so that we get to see the difference between transverse waves and longitudinal waves. But you would see that some of the key features, they might remain the same, just like the key feature which we are describing here as the what? As the wavelength, as well as the time period, as well as the frequency. But however, how we are going to be determining that, that is going to differ. So we want to see how they are going to differ. So thank you so much for being together. Let's meet in our next video, when we are now diving deep into what? Into longitudinal waves.